Okay. Well, now that we have been talking about joint distributions and joint densities, it's important to talk about how we can change variables when we have a joint distribution. Okay, so just like we saw in the univariate case, or in the case of a single random variable, there's a change of variables formula. So the change of variables formula we've already seen generalizes to joint distributions. We're going to talk about it here in the case of a pair of random variables. And that does generalize further beyond pairs of random variables, but we're going to just start here with pairs. Okay, so let's suppose we have random variables x1, x2 with a joint density. Write it as fx1, x2 on a region A. Okay, so be as arbitrary as we can be. And let's consider a transformation which takes each point in A to a point in B, some other region. Okay, so B is another region. A lot of times A and B might be the same, might just both be real numbers, but let's keep it general. And so we're going to define new random variables, a new function. Y1 is going to be g of x1, x2, g1 of x1, x2, and y2 will be g2 of x1, x2. So we're going to define two random variables from the previous random variables. So y1 and y2 are going to be random variables, just like x1 and x2 were, but y1 is going to be a function of x1 and x2. Y2 is going to be a function of x1 and x2. So one thing to realize here is that even if x1 and x2 are independent, it's possible that y1 and y2 won't be. So just to be clear what's going on here is we'll call this the region A. Within A, there's a point x1, x2, and there's a function g, which is just the pair of g1, g2, which takes, I won't be too sloppy about it, but I want to make sure that we realize that B is not the same as A necessarily. It's going to take us to this point here, which is G1, X1, X2, G2, X1, X2. Okay. So we're going to define from this the random variables Y1 to be that we process X1, X2 through G2, G1 and G2 respectively. So as long as G1 and G2 are smooth functions, we should expect Y1 and Y2 to have a joint density, just like X1 and X2. And so the question is, what is that joint density? So suppose for each point in the region B that y1 is g1 of x1, x2. y2 is g2 of x1, x2. Assume that this has a unique solution. So we're assuming an invertible transformation, which allows us to express x1 and x2 in terms of the pair y1, y2. So for each pair y1, y2 in the transform space, there's a unique point in the original space. And we write this as x1 is going to now be, well, it's G inverse. It's just x1 is going to be h1 y1, y2, x2 is h2 y1 and y2. Okay, then under certain conditions, and the conditions I'm not going to write because they're generally technical, but let's say, for example, that A and B are open sets, for example. Okay, so usually, for most of the cases we encounter, these conditions will be met. We do have to at least be aware that there are situations where this might not hold. You'd have to take a more advanced probability class to deal with that. But under those conditions, the pair of y1, y2 has a joint density. And the way that it's expressed is in terms of the original random variables, the joint density of x1, x2, evaluated at these two values here. So just to highlight these, right? This was x1 up here, right? So this is x1 and this is x2. Okay. Times, I'm gonna need to pull this over. It's big. Yo. Okay, times the absolute value of the determinant of, so it's called the Jacobian, the derivative of x1 with respect to y1, derivative of x1 with respect to y2, derivative of x2 dy1, partial derivatives dx2 dy2. Times the indicator that y1 and y2 are in the region B. So we're going to see, so this was like 1 over the derivative, or the derivative of the density in the previous, or derivative of H in the previous case. This is now going to look a little different here. The determinant, this is called the Jacobian. This is the Jacobian. Usually write it as J of x1, x2 is the Jacobian of H. Okay. We can also evaluate this Jacobian, this determinant of dx1 dy1 dx1 dy2 dx2 dy1 dx2 dy2 as 1 divided by the determinant of dy1 dx1 dy1 dx2 dy2 dx1. So you can either treat the rows or the columns. So the rows are indexed by x's, typically here. So the rows are indexed by the x's up here. And the columns are indexed by y's, and we're taking the derivative of the row but with respect to the derivative of the column label. We can flip it around, and in that case, we just have a 1 over the determinant. Okay. Okay. So this change of variables formula is actually pretty involved. Probably might look a little bit confusing, a little overwhelming at first, and that's certainly fine. We have several examples that we're going to be coming up with in the next couple of videos here, where we go through how a number of distributions that we already know, we can transform them through this change of variables formula, and we'll see how that all works out in the coming lectures.